Namaste and welcome back to the course on physics of nanomaterials. We have finished 5 weeks of this course. In the previous week, in the last lecture, I had indicated that we will now start learning about some very simple materials which are around us, but they have remained unexplored for many years or decades before they could come to the forefront of modern day technologies. And the first such material which we would start with, and you will find that these materials have large number of applications and there are huge number of industries which are just focusing on making new forms of such materials, and these materials are based on carbon. As we all know that we always talk about that human body is made up of carbon and hydrogen and oxygen, and you see the living beings around us, you see many of the vegetations, you see lot of biosystems, and you always say that they are made up of carbon. But you can clearly see that each of these systems which I am just mentioning, I am not giving you the whole gamut of such materials which are around us. Just a selected few, they also have very different response characteristics in terms of, let us say, external stimuli, force, that means their mechanical response is very different. They have different capacities to actually withstand heat, that means their thermal properties are different. They have different capacities to conduct electricity or even ions, that means they have different electrical properties. You even use carbon filters in your water purifiers, that means their capacities to attach bacteria, virus are also different. And if you see a column of a filter like that, you have carbons of different shapes and sizes stacked over each other. That means you have different types of carbons, even if they are in the powdered form, their capacities to capture, for example, bacteria also change, that means their chemical properties also change. And if you look around, you have systems which can be used as hair dye, that means you have their coating properties are different. You can have use of such carbon in toothpaste, that means when you make a colloidal solutions, then their properties are different. And you can use various forms of carbons, you can use in a cycle shoe brush. So, when you have this brake shoe bus, that is made up of carbon, and when you press that rubber presses the tire and reduces the speed of rotation, and your cycle slows down. That means they are also quite hard materials, and they can sustain severe shear forces, because you do not need to change your brake shoe carbon every day. That means they are quite hard also. So, at one end you are talking about very soft materials which are made up of carbon and used as die, and on the other you are talking about use of carbon based structures to make a brake shoe of a car or even cycle or any other vehicle which you want to slow down. So, just by changing the shape, the size, you find that the properties of these structures changes significantly. And therefore, let us start our discussion on carbon based nanostructures. And today I will start with our discussions on the carbon structures. And what are we going to focus on? We are going to focus on the structure, how versatile these structures are. You will find that these carbons change their properties appreciably by changing the hybridization states. You can get one of the most hardest material known till now as diamond to a very soft material like graphite, which you use in a pencil, or you can use a system which is having mechanical strength in between these two extremes, and that is called as carbene or carbine. So, you have the whole gamut of materials. Now, over the last 40 to 50 years, there has been a huge focus on carbon based structures, and newer forms of carbon nanostructures have been discovered, which have led to novel applications and huge use in today's electronics, to wearable electronics, automobiles to space, aircrafts to Formula 1 cars, and these structures have the capacity that their properties can be tuned as per the requirement of the end user. So, we will also talk about some of these structures. Talking about all these structures in this limited time may not be possible, but we will try to discuss some of the very important and commonly utilized structures such as fullerenes, carbon nanotubes, graphene and nano diamonds. And I have already talked to you that they have large number of applications. So, we will just give you an overview in today's lecture about the applications, and then there would be a detailed lecture in this week where we will just focus on the applications of carbon nanostructures in various fields. We will also talk about the synthesis protocols of some of these novel carbon structures which are finding large scale applications, and we will talk about the synthesis protocols of, let us say, graphene oxide or reduced graphene oxide. And you will find that these strategies are quite simple, provided you understand the importance of controlling the process parameters and maintaining the process in each cycle, so that reproducibility of these materials are ensured. So, as I said, carbon is an exceptionally versatile element, and you can obtain structures based on carbon both at the macroscopic as well as nanoscopic level. So, you can go from large size structures to very small sized materials which have tremendous confinement effects, and that has led to the discovery of various very interesting forms of carbon. Hence, now you talk about carbon structures which ranges from buckyball or fullerene type C60 material to 2D layered structures like graphene. And then you have tubular morphologies or traditional diamond and graphite based structures. So, just by tuning the shape, the size, you can change their properties, and hence they find large number of industries which are very interested to use them to develop newer technologies. So, if you look into carbon, what is it? In the ground state, you have a carbon in the electronic configuration 1s2, 2s2, 2p6. That means it has two unpaired electrons, and this can form just two bonds, which is insufficient for ensuring stability of the material. So, either the shell should be fully filled or half filled to ensure stability of the material. That is what we have read. So, now if you look into this case, you find that this is not what is happening. So, what happens? To form a half filled shells, carbon undergoes an excitation and promotes one of the 2s electrons to 2p level, and now you have these 4 unpaired electrons, but ensuring half filled shells, and so you ensure stability of the atom. What is next? These 4 orbitals will mix through to form 4 equivalent sp3 hybrid orbitals, and this will enable the tetrahedral bonding with a bond angle of 109.5 degrees, and that will give you the stable carbon atom. So, this is the basic of having stable carbon atom. Now, let us see what do we get when we place such structures in lattice or we tune the lattice which is formed by utilizing such carbon systems. So, if you look into diamond, you have a well defined lattice. What is happening? That you find sp3 hybridization. Now, if you go to structures which are actually layered structures. So, now you have carbon 2D structure, then another layer, then another layer. This means that you have carbon undergoing sp2 hybridization. How it will happen? It will mix 1 of 2s and 2 of 2p orbitals to form 3 sp2 hybrid orbitals, and each will contain 1 unpaired electron. And the 3 orbitals orient themselves at 120 degrees apart in a trigonal planar geometry, while the remaining unhybridized p orbital is perpendicular to the plane. What will happen? You will hence get these sp2 orbitals forming a sigma bond with 3 neighboring atoms. So, you have carbon, carbon, carbon and carbon, and the unhybridized p orbitals overlap side by side to form a pi bond, resulting in double bond. So, what will you get? You will get structures like ethylene C2H4, benzene C6H6 are typical examples of sp2 hybridized carbon atoms. So, you can have various forms of hybridization. So, you have sp3, sp2 or sp, and you can then have various fine forms of bonds forming between the adjacent atoms, resulting in stable long chain, planar or 3D structures. And clearly, just by looking at this arrangement given in these figures A, B and C, you can say that the response characteristics of these materials are going to be different. What is graphite which we have been using? Graphite is a sp2 hybridized carbon atom in a hexagonal pattern. So, in a hexagonal pattern, and what happens? Each atom is bonded to 3 others at 120 degrees with a bond length of approximately 1.42 angstrom. Now, the in plane sigma bonds, what will happen to them? The in plane sigma bonds in graphite are strong, while the pi bonds which is between the layers are weak. So, now if there are 2 layers, the bonding between 2 layers is weak, but the atoms within a layer bond quite strongly. Therefore, what can happen? You can easily slide the layers, which gives graphite, its lubricating or writing properties. And we already know that it is thermodynamically stable form of carbon and can be used as electrical conductor and also reflects light. You have different forms of graphite. You can have hexagonal or rhombohedral type stacking, and because of that you can see the layers are arranged in different manner over each other, and hence they get their mechanical, electrical or optical properties which are quite different. Now, if you see the third case, what is the third case? That you have an sp hybridization. What will happen in this case? In this case, you will have one of the 2s and one of the 2p orbitals getting mixed, and they will give you 2 sp hybrid orbitals, and these would align linearly with a bond angle of 180 degrees, so that they can have alternately single bond, triple bond, single bond, triple bond, so that the adjacent carbons are stabilizing in the electronically stable configurations. The remaining 2 unhybridized p orbitals would be perpendicular and can form pi bonds, similar to what we saw in graphite. And because of this triple bond of 1 sigma and 2 pi bonds, you get molecules like acetylene or carbene, which have different properties than graphite or diamond. And such structures are extensively studied now. These carbenes are also classified as humulines, which can have successive double bonds, or polyenes with alternating single and triple bonds, so that carbon becomes stable. So, now you can see, just by changing the arrangement of carbon atoms, you can get different types of hybridization, and by changing the types of hybridization you can get different types of materials which will have very different properties in comparison to other materials that had a different type of hybridization. So, while sp2 and sp3 based materials are very well understood, creating the structures where you have sp type hybridization is slightly difficult, because they tend to undergo cross linking, and this makes it a challenging task to even isolate or stabilize them in pure form for long periods. And hence you have to sometimes create a synthesis protocol where you also use a non-reactive terminal groups which can prevent such kind of cross linking. Now, let us see why these structures which have been investigated over the last 40 to 50 years have become so important? We have seen that clearly by just changing the order of hybridization, the nature of hybridization, you will get different atomic arrangements and newer forms of carbon structures are expected. So, what are those types of structures which have been synthesized and are now being utilized? We have structures like fullerenes, nanotubes, graphene and ribbons, and nanodiamonds which have been stabilized. They have different types of freedom in their structures. So, in a tubular morphology, you have 1D type freedom. In graphene, you have 2-dimensional freedom for electron, whereas in fullerenes, you see significant confinement in all the 3 directions. And nanodiamonds, although there is freedom, but you have these nanodiamonds arranging themselves in a bulk form, but because the building blocks are nano sized, as we have seen in the first week, the properties are very different from those which we expect from diamonds of larger sized. So, just by looking at these structures, you can clearly see they are very different. But please remember, the atom which we are focusing is still carbon. It is made up of carbon. All these structures are just made up of carbon. So, what do you expect? Their properties are going to be different, and hence they are finding large application in various technologies which are utilizing nano sized particles to obtain new application ranges. Let us start with fullerenes. This Buckminster fullerene, which is having 60 of carbon atoms, was discovered in 1985, and it has a truncated icosahedron with 60 vertices, 32 faces, consisting of 12 hexagons and 12 pentagons, where each of the carbon atom lies at a vertex. So, what kind of structure do you see? This is similar structures which you see in a very stable football. These are the structures which are actually simulated. You see these hexagons and 12 pentagons which are arranged in a football, and these structures are extremely stable. In such cases, in Buckminster fullerene, the carbon atoms are actually covalently bonded to 3 neighbors using sp2 plus delta hybridization, where delta accounting for the curvature induced distortion. So, now you have a spherical shape. Now, if you have a spherical shape, the charge distribution on the surface is different, and therefore, you need to have charge sharing in a way that overall charge neutrality condition is maintained, and hence you have this hybridization where there is some curvature induced distortions, and hence that has to be accounted for. Typically, the average bond length is approximately 1.46 angstrom with 5 membered rings, and it is approximately 1.4 angstrom between 5 and 6 membered rings. So, we are talking about the structures and how do they link to each other. Now, if you have these slightly modified ring structures, you will try to bond them, and then there would be strain due to this ring structure, and that will lead to slight variations in this bond length because of this strain which is coming from the structures. And amongst these C60 structures, the buckyball structure is most stable and extensively used. They are very, very stable structures. Then came the discovery of graphitic onions, which were very similar to fullerene like structures, and we had such structures having only pentagonal and hexagonal carbon rings. So, they were like onion structures. Now, these were found to be quasi spherical nanoparticles. So, they were not exactly spherical, they appeared to be spherical, made up of concentric graphitic layers enclosing carbon. So, you had layer over layer over layer, and this was resembling nested fullerenes, and therefore, you called them as onion structures, because in onion also you can peel out one layer at a time. So, this was called as graphitic onion. As you can see that because of this dominant layering, you will find that compared to fullerene, the way these structures will give electronic and mechanical response would be different from other carbon structures. Then came a structure which was later called as carbon nanotube, which was called as carbon fiber in 1976, and later it was called as carbon nanotube in 1991 by Ijima. So, you can see it is a tubular morphology, but if you have many tubes nested, or you have this arrangement of tubes, then there is another tube of larger size over it, and then you call them as multi-walled carbon nanotube. And this was discovered when there was an attempt to synthesize carbon structures more towards the C60 structures using arc method. And when the synthesis was carried out, then the TM showed that there were certain particles which showed tubular morphology, contrary to what was expected. There was an attempt to make a buckyball like structures, but you were getting tubular morphologies, and when these properties of such materials were investigated, they had very different response characteristics, and hence they themselves became very important, and the name was given as carbon nanotubes. The chiral angle in such carbon nanotubes, that is the way they are actually rolled. So, how do you roll these sheet like structure? So, if you take a plain piece of paper and roll it, then how do you roll this structure will give you a tubular morphology, and this tubular morphology, if it is not exactly cylindrical in shape, if you have like a square tube or any other kind of tube, they will have a different electronic properties or mechanical properties. And so, the chiral angle also resulted in different forms of carbon nanotubes. And you could see that because of the van der Waals forces and pi stacking in such layered structures, what were you getting? That the nanotubes could actually give you ropes or bundle like structures. And if you have such structures, their properties are going to be different. And post the discovery of fullerenes and carbon nanotubes, now practically you see new forms of carbon reported on routine basis. Some of them can be like nanocones, nanopods, nanohorns, toroidal carbon rings, or spherical carbon structures which are having similar morphologies to those of fullerenes or carbon nanotubes, but their response characteristics are very different. Then came the discovery of graphene in 2004, and this is now not a three-dimensional structure which we are talking about a layered structure. So, we are talking about a plane where carbon structures are arranged in a hexagonal lattice. So, we take the layer of carbon structures, and what do you expect in such layered structures? So, if you take these freestanding sheets which was actually accidentally discovered, that you had the carbon powders and from there a Scotch tape was stuck to it, and when to peel out the carbon structures, single layer of carbon structures were getting peeled off, and that method was called as Scotch tape method, and that is called as mechanical exfoliation. One layer is being taken out each time. So, exfoliation. So, this was seen. Now, you do not have the tubular morphologies, but you have an open structure. So, now if I say that you take a piece of paper and then you do not roll it. If you roll it, connect the end to end, you get a tubular like morphology. Just keep the paper flat. Is the property of the flat paper, that is a two-dimensional structure, and that of a cone, are they same? You can immediately see that no, they are not same, and hence you can then extrapolate that understanding that when you go from a tubular type structure to a planar like structure, the properties are very different. And it has been seen that their carrier mobilities are different. They also have low resistivity, which was unmatched by materials before the discovery of graphene. So, they had a very low resistivity, and because of this quantum confinement effects, they exhibit quantum transport properties and leading to anomalous Hall effects and behavior like relativistic particles. This has made them useful for high speed electronics, sensors, nano devices, energy devices, energy storage devices, and therefore, they are outperforming traditional materials like silicon. Then you have not just one layer, but you have graphene oxide, which is a modified form of graphene which contains oxygen as functional groups. and you can synthesize them using simple Hammer's method. And because of this hydrophilic nature, GO is highly dispersible in water and many solvent, unlike pristine graphene, and that gives you the capacity to process and fabricate large area films, coatings and composite materials using graphene oxide. Now, the next material is reduced graphene oxide. Here, graphene oxide is electrically insulating or semiconductor, but you can also reduce it, and this is called as reduced graphene oxide by partially removing the oxygen groups from the GO lattice, and this can be done using thermal, chemical or electrochemical processes. And because of this, you change the charge conditions in this structure, which allows the utilization of RGO for energy storage or sensing applications. And synthesis of GO and RGO is more scalable, and nowadays it has become quite cost effective also in comparison to pristine graphene. For example, you can make GO using a modified Hammer's method, and the reaction is very simple. You just have to take, let us say for example, graphite powder in the desired stoichiometric ratio, then you have the corresponding H2SO4 and H3PO4 added to it, then you add KMnO4, you get a brown slurry, then add H2O2, finally you get a yellow like structure which indicates formation of GO. Now you centrifuge, wash with a washing solution which can be water or it can be ethanol or water and ethanol alternatively. So, depending upon what kind of washing you are taking place for these particles, then dry them and you get a GO powder. Using this GO powder, you can now easily get RGO. Just take GO, ultrasonicate, add the desired NaBH4, heat it at temperatures between 80 to 100 degrees, let it cool for 24 hours, you centrifuge and dry, you get a reduced graphene oxide. So, it is a very simple process, and if you now compare what do you get, just look at the X-ray diffraction of these structures, or you see the Raman spectra of these structures. You can clearly see multi-wall carbon nanotube compared to RGO, compared to GO, compared to graphite. The kind of crystallinity you induce in these structures are very different. So, the crystallinity changes from one type of material to the other, and the moment there is change in the nature of crystallinity, what will happen? The atomic arrangements will change, and hence everything which we have talked about in the first 2 weeks will come into picture, and you can easily expect modulation in electrical and optical properties. The nature of bond lengths also change in these structures as shown by the Raman peak, and hence you can claim that the chemical properties of these structures would also change. And here you can see the flake like layered structures of RGO which are stacked over each other. So, they are not particles, they are like papers after papers after papers stacked over each other, and that is what a RGO looks like. So, today we have given you an introduction to carbon based nanostructures, how do they change as the hybridization changes, and we have also introduced some of the types of carbon based materials which are being extensively used in industries. You can find more detailed information about these structures in these references, which I suggest you can go through to have even more detailed information about the topic which we are going to cover in this week. So, I thank you for attending lecture 1 of week 6.